Hi, I'm Amanda Olson, and we are looking at problem 2.6, number 12. So this problem says a fish is reeled in at a rate of 2.8 feet per second from a point 10 feet above the water. At what rate is the angle between the line and the water changing when there is a total of 25 feet of line out? So some things that we need to define, and the textbook is really great about giving us this visual. We've got this angle theta, and then we have this 10 feet above the water, that's going to remain constant. This x is the line out. So this would be when x equals 10 feet above the water. That's sort of our y, we could think of it. This would be y equals 10. And then the fish is reeled in. Well, the length of that, the reel, that we can call x. And so we're really looking at it when x is 25 or 25 feet. I'm going to just omit units for a little bit. And then the angle between the line and the water, we want to know what that's changing. So that angle is going to change with respect to time. So we have that angle, and then what we want is we want to find d theta dt. What we're given is that we have x is equal to 25, y is equal to 10, and the rate of change of x, since we defined x to be the real, is going to be that dx dt. We're given that that's changing at a rate of 2.8 feet per second. So when you see that rate of in calculus, you can think of that being a derivative. If you have a rate of change of any sort, that's usually going to be the derivative with respect to time. So we know that this is 2.8. And again, I'm just going to omit for right now, just for simplicity, I'm going to omit the units of measure. Okay, so we know what we want, we know what we're given. Then it can be kind of nice to lay out an equation. Now this one, we're not given an equation, so we kind of have to use some of our background information. I see a right triangle. If I look at the directly above the water, assuming the water is perfectly horizontal, I have that right angle. So that tells me I'm dealing with a right triangle. From there, we know we have a couple different sides. I'm not really given a lot of information about this base. So that's kind of hard to work with, but we do have this left side, and then on the right triangle, what would be the hypotenuse. So I do know if I'm dealing with a hypotenuse, which in this case is our x, and then for my angle theta, I have the opposite side. Then I have this relationship between x and theta, which is that sine of theta equals the opposite over the hypotenuse, or sine of theta equals 10 over x. So now we have our equation, and we really want to find that d theta. Right now, we don't have theta explicitly, so we have to use, without theta explicitly, we have to use implicit differentiation. We could solve it for theta, but that's going to get a little bit tricky because then you're taking the sine inverse, and we haven't talked about derivative of sine inverse. So let's just not make it that complicated. Let's just use implicit differentiation. So remember, x is changing with respect to time. So we want to think of x as a function of time. And we're going to differentiate, because we're looking for d theta dt, I'm going to differentiate both sides with respect to t. So theta is a function of t, x is a function of t. I'm going to differentiate both sides with respect to t. Okay, when I do that, finding the derivative of sine of theta, since theta is a function of t, we have the chain rule applying, because we have that theta function, which is a function in terms of t, and then in the theta function's inside another function. So we take the derivative of the outer function, which gives us cosine theta, and then we need to multiply by the derivative of the inside function. So this is going to be multiplying by that d theta dt. We don't know what theta is in terms of t, so we just leave it as d theta dt. From there, the right-hand side, it looks like, you're like, well, we could use the quotient rule. If you didn't want to use the quotient rule, you might recognize that this right-hand side is actually equivalent to 10x to the -1, okay? And then you can just use your power rule. A lot of times, we don't want to use the quotient rule if we don't have to, and since we can write it easily as an exponential, I would prefer to write it as 10 times x to the -1. If you use the quotient rule, you'll get the same result because the derivative of 10 with respect to t is going to be 0. But using that power rule, then on my right-hand side, I get a negative. Let me change my color. I get a negative 10x to the -2. But then remember, x is a function of t, so I need to multiply by the x dt. All right. So now we can just kind of isolate the d theta dt, and we can do that by dividing both sides by cosine. So from there, I have -10. This x to the -2 power, I can put it in the denominator, so I get x squared. And then I'm going to have also, because I'm going to divide both sides by cosine theta, I'm going to have that cosine theta in the denominator. And then I'm going to have the x dt. Okay. So finding cosine of theta, there are some ways you can do that. One of them is you could figure out, okay, well, what is theta if x is 25 and y is 10? That's one way to do it. Another way is to use some of your trig background. Okay, so we know that we have this right triangle, and we know that cosine for theta, cosine of theta is going to be equal to the adjacent over the hypotenuse. Now, we're not given any information about the adjacent and hypotenuse, but we could find the adjacent because it is a right triangle and we know x. We could use, the fact that the adjacent, if we use the Pythagorean theorem, this is going to be the square root of 10, x squared minus 10. So that would end up being our adjacent, and that's going to take up the numerator of my cosine theta, and then my denominator would be the hypotenuse, which is just x. That's one way to do it. Another way is to, like I said, solve, use the sine inverse function, solve for theta explicitly, and then plug that into the cosine function and go from there. Whichever way you do it, I like to stick with the variables x and that sort of thing. So I'm just going to go that route. So what that ends up with is that we have that cosine of theta, which is equal to the adjacent for this triangle. So that's going to be the square root of x squared minus 100 over the hypotenuse, which is just x. Okay. So now we can go and kind of plug in some values that we know. Of course, we don't know d theta, dt. We have -10. Here, since cosine theta is in the denominator, I'm going to go ahead and flip this to be cosine inverse, or the inverse cosine. You could also have even recognized that 1 over cosine is secant. There's a lot of ways you can do this. It's just kind of working out the algebra, and there's quite a few different ways to do that. Okay, again, so I have cosine theta in the denominator, and rather than making a complex fraction and putting that whole square root, in the denominator, I'm just going to multiply by the reciprocal. Again, your algebra might be worked out slightly different, and that's okay. You're going to get the same result in the end. Of course, I love that dx dt, and you could simplify that at any point. All right, so then some things that I see that cancel. Of course, we have an x that cancels. So I'm left with, on my right-hand side, d theta dt is equal to -10 over the square root of x squared minus 100 and times dx dt. Okay, so now I'm going to plug in my specific ones because I'm looking for a rate of change at a specific point in time. So I'm going to plug in my 25 for x. I'm going to plug in my 2.8 for my dx dt. And really, because this dx dt is it's going down, it's being reeled in, and so that reel is going to get smaller and smaller. We really want to think of that dx dt as a negative because it's decreasing x. So that's just one thing to note. So from there, I have 28 over the square root of 525 . Okay, and I just realized I dropped the x over here and I never put that back in. So I'm just gonna go back and put that there. And so we've got this x in the denominator here, so note that. Then how that's gonna affect is we're gonna have a 25 outside of here, 25, and that's gonna affect our calculations, d theta dt. And so if we work all that out, we get approximately 0.04, and it said 3 decimal places, I believe. So I get 488, so about 0.049. And then this is just going to be radians per second. Right. Okay, so hopefully that kind of clears things up. And again, sorry about that mistake. So then our final answer is 0.049 radians per second. Okay, thank you.